Hey guys, today we're starting our new unit where we're going to be talking about our sound characteristics. In this case, we're going to start with talking about our base wave equation, and we are going to use that and determine velocity in different medium in order to figure out our wave characteristics. And the second thing we are going to talk about is we are going to talk about intensity and intensity of sound, how loud it is, and how we can work with those units as well. So with that, for today's problem, I have a guitar string that I am plucking in such a way that it is going to oscillate. And I am told that this oscillation, I want to create a sound with a frequency of 110 hertz. And I'm told that in order to do that, I have this piece of string that has an overall length of 63.5 centimeters. Now that length doesn't actually mean a ton to me. We will do some stuff with it later in the unit, but not quite today. What I do want from it is I would like to know my wavelength. And if we think about our base sine wave, this is one full wave. And what we're seeing here is just 1/2 of that wave. We're seeing that first up or the first down, depending on where our piece is sitting. So in this case, when we're talking about our guitar string, our wavelength is going to be double our overall length, which we're given as 63.5. So that is 127 centimeters. Or it's going to be easier for us if we are working in meters, so 1.27 meters. And the last thing we're given is we are given a linear density. And that linear density we are given is basically how much any given length of this guitar string weighs, which in this case is 7.20 grams per meter long. So if I had a meter long guitar string, it would weigh 7.2 grams. In this case, I still want it to be in my more normal units, so I'm going to convert it to kilograms. So I've got 7.2 times 10 negative third kilograms per meter. Okay. What we want to find with this information? Well, there are a big list of things that we need for this problem. I am going to kind of break it down into 2 to 3 different options. And the first thing that we're going to do is just using this piece. We are going to get a little bit more information in a second. But to start, we just want to know how much force are we required to have pulling on either end of the string. What is our tension, our force tension, required in order to make this frequency, given this string? Now, with that, we don't actually have an equation that relates our force tension to our frequency. What we do have is an equation that is specific for a string locked on both ends, saying that the velocity of a wave on that string is going to be equal to the square root of the force of tension acting on the string divided by the linear density of the string. And that's getting us to the velocity of the wave, not the velocity of the wave on the string specifically, not the frequency or anything else we have here. However, at that point, we do have enough information because our base wave equation says the velocity of a wave, so in this case, the velocity of our wave on our string, is going to be equal to the frequency of that wave multiplied by the wavelength of that wave. So we do have the wavelength, we do have the frequency, we can get this velocity along the string, which means we can get this force tension. So for that, our velocity along the string is going to have to be equal to 110 hertz, which are units of 1/seconds, or cycles per second, times our wavelength, and our wavelength is 1.27 meters. Meters times 1/2 is going to be meters per second, which are units of velocity. And that gives me a value of 139.7 meters per second. I'm going to go ahead and I'm going to throw that down here. I'm not going to need it for equations in the future, other than this guy right up here, but it is going to be a nice comparison point in a second. So 139 meters per second. Now with this, I need to solve this guy for the force tension, so I'm going to square both sides. So I've got force tension is going to be velocity of the string squared, and then currently I've got a divided by mu on this side, so I'm going to have to multiply both sides by that linear density, and that is going to give me my tension force. Solving this is just 139.7 meters per second squared multiplied by my 7.2 times 10 to the -3, I've got space, kilograms per meter. And double checking units here, I have meters per second squared, so I've got meters squared per second squared, multiplying that by kilograms per meter. Meters cancel out one of the meters squared. I get kilogram meter per second squared. That is a Newton, and a Newton is a unit of force. So this sure looks like it's going to give me a force. That force comes out to 140.5 newtons. And that is what I'm looking for. Perfect. Okay, next thing. We have that force. We're told that this guitar string exists on a stage over here. And I'm going to draw it smaller here. So I've got my guitar string, which is oscillating, and it is creating some sound. And that sound is going to travel like so, away from it. It's actually going to go in multiple different directions. But we're told that that intensity of that sound, when we have moved 5 meters away from it, so I've got something right here. At this point, our intensity of sound has a value of, 80 decibels. Okay, and what we want to know is I have way over here, I'm going to run into that black square again. Way over here, I have a microphone that has a square detector, and it is a total of 91.5 meters away. I believe that is a football field, is what I have it set up as. It's 91.5 meters away, and it's going to have a detector that has a size of 3 centimeters by 3 centimeters. That's the total detector area. All the sound that's hitting this, any of these little pieces that make it, are all being added up. And that's all being recorded by this microphone. Okay, what I want to find from this. I'm going to label these locations as I'm going to label this as location A, this is location B, and the microphone as location C. I would like to know, if this is true, how much power am I putting out into the world from this guitar string at location A in order to create an intensity of 80 decibels at location B. Next thing I want to know is what is my intensity, and I would like to know intensity in the units that people actually work with. So decibels at location C, and I would like to know the power, thinking intensity still, the power that is being picked up by the microphone at location C. So we know it's producing a certain amount of power at location A. How much is actually getting picked up by the microphone? How much is the microphone absorbing? Okay. Let's get started with that. So, my power at A. I know I'm going to be using this 80 decibels to get there. And the thing about decibels is we can't work with decibels in any of our equations. The only thing we can do with decibels is convert out of them. Decibels are a lovely unit. They are a log scale, which means that we can cover a large range of sound because there's a large range of sound intensities with a single number without having huge, ridiculous, weird numbers. However, it means that we can't just plug them into our basic physics calculations. So with this, first thing I need to do is get out of decibels. So I know the equation for decibels. 1 decibel is 10 times the log, and this is the base log. This is a log 10, base 10, which is what you get from just hitting log in your calculator, of my intensity actual, and this is going to be in whatever units that I put my intensity naught in. And in my intensity naught is that set value that is a constant, kind of like gravity is a constant normally. We do have the gravitational gravity, but normally it's just a number that we're plugging in. That I naught is a number that we're plugging in. It's a constant for our sound-based pieces. Well, for decibel conversion, really. With this, I have this value. This is a constant. I want this value. So I'm going to go ahead and start solving for it. So first thing I'm going to do is I'm going to move that 10 over to the other side. And then I want to get rid of this log base 10. You may recall from math that log is the opposite of an exponent. So if I put both sides up to the power of 10, so I say that this is 10 to the power of this divided by 10, that is going to get rid of the 10. So 10 to the log 10 is just going to give me the final value there, meaning that I can solve for intensity at that point. And my intensity, sorry, I've got limited board space here, is going to be my I naught times 10 to the decibel level divided by 10. And in this case, my intensity, I want that 80 decibels converted. My intensity is going to be equal to I naught, which is going to be 10 to the negative 12th watts per meter squared times 10 to the 80 decibels divided by 10. So 10 to the negative 12th times 10 to the 8th is going to be 10 to the negative 4th watts per meter squared. I'm going to go ahead and throw this guy up here because we will use him again. 10 to the negative 4th watts per meter squared. And then we know that how sound dissipates, it's dissipating out in a sphere. So we've got the sound waves going in all directions, kind of like what I have drawn right here. Technically, you can hear the guitar from behind the guitar, so we've got the arrows going back as well off the board, as you guys can see it, unfortunately. But we need to have all that in consideration, and it's going to go into the board and out of the board as well. So we are going to use our intensity equation. And our intensity equation is our, let's switch markers here. My intensity is going to be equal to the power that I'm putting out into the universe divided by the area that that power is split up over. And that just has to do with our intensity units. Watts are units of power. Area is units of meters squared. Intensity is power, is watts per meter squared. Power per unit area. Now I want to solve for power, so I'm going to say my power is going to be equal to my intensity times the area that has been spread over. And the area that has been spread over is the surface area of a sphere. So I've got intensity times 4 pi r squared. It's going to be the area of my sphere, the surface area of my sphere, not everything in between. It's anything at a distance of r. So my power is going to be my intensity, which is 10 to the negative 4th watts per meter squared, times 4 times pi times my radius. I am 5 meters away, squared. Oh, this is meters, 5 meters. So the meters squared and the meters squared are going to cancel. I am going to get a value for my power supplied of 0.0314 watts. And that is my power a day, so 0.0314 watts. Okay, that's done. So we solved for position A. Now we need to solve for position C. I've got two options at this point. The first option is just to put in right away again, my I is going to be equal to my power divided by my area. My area is 4 pi radius squared, and my radius is now 91.5. That would solve the problem for us. That is what we just did, however, and I want to show off a slightly different equation. So I'm going to go ahead and use a different one. So I know my intensity at point B. I want my intensity at point C. What I can do is I can create a comparison equation. So what I'm going to do is I'm going to say my intensity at point B divided by my intensity at point A, at point C, is going to be equal to my radius at point C squared divided by my radius at point B squared. And that means that if I solve all of this for my intensity at point C, I'm going to get a value of, I have radius at C, I think I'm backwards there. I've got my radius at B squared divided by my radius at C squared multiplied by my intensity at B. Because that would be IC divided by IB is equal to RB squared over RC squared. Perfect. So my intensity at point C is simply going to be my radius at B. My radius at B is 5 meters squared divided by my radius at C. That's 91.5 meters squared multiplied by intensity at B. That is 10 to the negative 4th watts per meter squared. And there we have it. that is going to be a plug and chug calculation, and it will give me a value of 2.99 times 10 to the minus 7th watts per meter squared. However, this is an intensity in watts per meter squared. I want a intensity as a decibel level. So I need to convert this IC back into decibels. And I think I've got enough room on the bottom. We'll move over just in case I need a little bit more. So my decibel level at C is going to be equal to 10 times the log base 10 of my I, which is 2.99 times 10 to the minus 7th watts per meter squared, divided by my I naught, which is 10 to the negative 12th watts per meter squared. That is my equation for my decibel level. And when I plug that guy in, I get a value of 54.75 decibels. Hopefully you can see how this is a much easier number to work with than that if you're actually going to label things. So great news there. That's why we use decibels, 54.75 decibels. Okay, last piece before we add something extra to the problem. I want to know what my power at C is. What is my power that's actually being absorbed by this microphone? So we did power before, is what is the power expelled by the string. Now we're talking about the power that is being absorbed by the microphone. So for this, what I am going to do is exactly the same thing. Intensity is power divided by area. So in this case, I have my intensity, I have my area, because it's how many of those little squiggly lines are going through my little square piece that I have up here that is my microphone inlet, and I can figure out that power. So power at C is going to be my intensity at C times the area of my microphone, which is at point C. Area of the microphone is just going to be 3 centimeters by 3 centimeters. IC I just had written out before I converted it to decibels. Again, I don't use the decibel value. I need to use the watts per meter squared value in order to make units work here. And that value was 2.99 times 10 to the minus 7th watts per meter squared. My area is going to be 3 centimeters times 3 centimeters, or 0.03 meters times 0.03 meters. I'm going to just write it as 0.03 meters squared just because I don't have enough board left here. And that will give me a power value for the power absorbed by this microphone of 2.69 times 10 to the minus 10th watts. So this guy is 2.69 times 10 to the minus 10th watts. Oop, I'm a little off the board there. Let me try again here. 2.69 times 10 to the minus 10th watts. There we go. Okay. Is that all I have for you? No, not quite. Last thing, we're going to go back to talking about the speed. And we're going to say that we have a day with 20-degree Celsius weather. And I want to know how long it is going to take for the sound to go from A to C? How long is it going to take my sound wave to make it all the way there? And for that, first thing I'm going to have to find is I'm going to have to find my velocity of my sound wave in air. So velocity is going to be equal to frequency times, oops, I don't need it, sorry. Velocity, I'm jumping to the wrong piece. Velocity in air, we are given a special equation that is based off of the velocity in air at different temperatures of air, which impacts it ever so slightly. And that is going to be equal to my speed of, my base speed of 331 meters per second divided by times the square root of my temperature divided by my temperature at 0 degrees Celsius, or 273.15 Kelvin. Okay, and this velocity, this 331 meters per second, that is the velocity at 0 degrees Celsius. That's the velocity of air of sound in air at 331. So in this case, my velocity in the air is going to be 331 meters per second times the square root. This is not 20. We need units to cancel. This is in Kelvin. And when we're using equations like this, where we're dividing or multiplying or whatever with temperatures, we have to be in Kelvin. And I think most of you guys have taken chemistry and a bunch of it, so hopefully pretty used to that. But it's coming back in physics, so if you hate it in chemistry, I'm sorry. That is going to give me a value, 20 degrees Celsius is 293.15 Kelvin. Divided by 273.15 Kelvin. It's going to give me a velocity in air of 342.9 meters per second. That is velocity in air, considering the air is at 20 degrees Celsius. How long does it take to get from here to here, going 342.9 meters per second? Well, that is just getting back to kinematics. Velocity is equal to our, well, actually, position final is equal to position initial plus velocity times time plus 1/2 acceleration times time squared. We don't have any acceleration going on here, and we just want to know the delta x. So delta x is going to be our, sorry, not our delta x, our time. Time is going to be equal to our delta x divided by our velocity. So I have a distance that I'm traveling of 91.5 meters. I have a velocity that I'm going at of 342.9 meters per second. Meters cancel, 1 over seconds. 1 over 1 over seconds is seconds, so I get a value in seconds. And it is going to take 0.267 seconds between when this guitar string is strung and when the microphone that is a football field away hears it. That is most of what I want to solve for in this problem. I do want to go ahead and take a second to look at a couple of things. First of all, we've got two velocities here. Velocity of sound in air and velocity of sound on the string. You notice that these velocities are very different. The sound is traveling much faster when it's just traveling through air. It's a much easier medium to move through. Second thing I want to compare, and the more important one, is I want to go back and I would like to look at what our wavelength of our piece is in air. So we know that velocity is equal to frequency times wavelength. And the frequency, so this piece is oscillating, and each of those little oscillations creates a shock wave, which is creating the sound, which is moving through the air. So those oscillations, the frequency here is on the string is the same as the frequency in the air. So our frequency is still 110 hertz. However, this velocity is changing, which means that the wavelength in air is actually different than the wavelength on the string. So if I wanted to know this wavelength in air, what I would do is I would go ahead and I would solve this equation for wavelength. I would say it's going to be velocity divided by my frequency. I know that my velocity is 342.9 meters per second. I know that my frequency is 110 hertz. That is going to give me a wavelength in air of 3.12 meters. So the wavelength of these compression waves in air is 3.12 meters. The wavelength on the string is 1.27 meters. We have a different wavelength because we have a different velocity. So something to keep in mind of, something to keep track of. Hopefully that was helpful. See you next time.